It's example 1 in a polynomial set of examples. I'll have a few polynomials. P1 will be like this, 1 plus 2x. P2 will be minus 2 minus x. P3 is minus 8 minus 10x. And the Q, I changed the name to Q, 8 plus 13x. That will be the one we're going to be testing whether it belongs to a span. Okay? Again, when you address this question, everything starts with definition. You say, we aim to find the unknowns, lambda 1, lambda 2, lambda 3, such that if you take the combination of your P polynomials, the result will be Q. Again, it will help a lot if you will do parallels with the way we've done linear dependence independence with polynomials today. So you replace your polynomials with what you have for those polynomials. This is a substitute for P1. This is a substitute for P2. This is a substitute for P3. This is a Q. Again, we approach this from the point of view that this is true for any x, because we effectively we're looking at the identity between two functions, and we claim that these functions are identical. So this polynomial function identically equals to this polynomial function. We rearrange. So it's a linear polynomials on either side. So we collect all of the free terms, 1 lambda 1, negative 2 lambda 2, negative 8 lambda 3. And x terms are 2 lambda 1 here, negative lambda 2 here, negative 10 lambda 3 here. That's fine. And that's my right-hand side. And at this stage, we're going to engage again this result from the first year math, which says if you have two polynomials equal identically for every x, you can claim that coefficients of those polynomials are equal one to another. Like a free coefficient on this side equals to free coefficient on this side. X coefficient on this side combined complete x coefficient on this side equals to x coefficient on this side. And that brings up the system of linear equations. Free coefficient equals to 8, first equation. X coefficient equals 13, second equation. Again, we do it under the target that we have to answer whether we can find lambdas, which works like this. In terms of the system, we're looking for the solution of this system, whether this system is solvable. It's row echelon form. Once again, we struck the augmented matrix. This is my augmented matrix, left-hand side, right-hand side. We convert this to the row echelon form. These are my steps. Oh, sorry. I hide the steps as I always do now. It's only one step actually. It's because it's only two rows here. So you have to do only one step to convert this to the row echelon form. And again, we analyze where the pivots are. We have two rows, so we will have at most two pivots, and we can spot them on the left-hand side, 1 and 3. Hence, my system is solvable, and hence the answer here is yes. Originally, it was under the question mark, but now, after we found the row echelon form, the answer is yes. The answer is yes. If the question was just to answer whether your Q belongs to a span, you can stop at this stage. If you're actually looking for those lambdas, you will need to back substitute to identify a set of such coefficients. And again, you don't have to do it in a general form. You don't have to find parametric solution. You can start with any solution of your liking. So I told you before, because it's not a linear dependence independence question, you don't have to take 1 in place of a parameter. You can take 0. But in this example, I actually took 1 just for a change. You can take 0. That will work as well, because we're not aim to find non-zero solution here. It's not a linear dependence independence question. So if you stressed for time, 0 will be the most optimal choice, almost for sure. But I just choose 1 just to have a difference. So you chose the unknown for the non-leading column, and then you solve for the rest of the leading unknowns. I solve from here for lambda 3, right? I mean, just move this 3 and 6 on the other side. Actually, I forgot to divide by 3 here. I just realized that. I mean, this is an incorrect solution. I need to divide everything by 1/3. Should be like this. And that will be -3 then, not -9 as originally typed. And then my lambda 1, let's just see if I made any mistakes here. So I have to move these two on the other side. It will be 8 plus 8, right, because this is 1. And then I made a mistake here. It should be not -2, it should be -6. So the result actually not -2, but 10. That's the correct coefficient. Yeah. Any objections to my arithmetic? So we can express my Q polynomial as a combination of my P polynomials, even though I have to correct my coefficients. It should be -3 here, and it should be 10 in here. This is the expression for that Q. You always have a double check here. I mean, after you found these coefficients, you can actually double check whether they truly work. You can go back to your polynomials and see if it works for you. I neglected this option when I was putting this slide together. I had some excuses, of course, but you won't have them when you do tests or exams. So don't neglect double check. Any questions? Yeah. And that's how you frame questions for span with polynomials. Again, sometimes you have it like what will happen sometimes. So when you jump from here down to the metrics, sometimes people do to cut corners and save some time. Again, pay attention that the coefficients of your polynomials, they arrange in columns, not rows. This is a very frequent mistake. Oh, that's right. That's right. Absolutely, absolutely right. That's not a typo. Yeah, it should be 10 here. I just arranged them in the other way. Yes. Absolutely. Thank you very much. Nice spot. Nice spotting, I should say. Any other objections?